Let's jump into it. We're in book 2, elementary analysis. I believe we're in section 2. We were talking about some of the rational numbers. We already know what these are, so we're just looking at some properties of them, and we ended with the rational roots of them. Which says, if R in Q is a solution to the polynomial I think you see it, but it doesn't matter. X to the n minus 1 plus a1x plus a0 equals 0, where the ai are integers, then R has the form it will be a factor of the a naught divided by a factor of the a. So, yeah, that's concise record, but I think that says all the important things. So any rational root to a, and of course, we can assume, I'm thinking of this will also work if the coefficients are also rational. You just clear the denominators and then apply this. But assuming that we have a polynomial with all integer coefficients, then notice that if a rational number solves this equation, it must have this form. And so, I'm not going to write out the proof of this, but it's really not hard to prove. If you just assume that R equals, say, P over Q, you know, the usual things, fully reduced. Q not equal to 0, PQ integers. Then, knowing that that's a solution means if you plug in P over Q for X, it will solve this equation. Basically multiply through by the LCD to clear all denominators. If you solve for the term of the highest power, you'll be able to factor out Q. If you solve for the term of the lowest power, you'll be able to factor out P. And it'll show you that this and this will divide R respectively. And so we're going to skip the proof of that. And you've used this before when factoring quadratics, right? So if you had to factor something like so we know that the roots of that, you'll notice, you guys know what they are, right? What are the roots here?
3 and 2.
Well, minus 3 and minus 2, right? Now, you notice that those both divide into 6. That wasn't a coincidence. That's a consequence of this theorem, right? So when you start to think of all the terms, and this, you also use this fact when you were learning how to factor cubics, and you couldn't factor it, so what you did was you guessed the number that if you plug in you get 0, and you always guess the factor of the last one if the coefficient was 1. And this is the reason why this theorem was working in the background. As a corollary to this, if the polynomial is monic, i.e. an equals 1, then any rational root is a factor of a naught, right? So you always write r as plus or minus a naught, right? Which is would apply to the example that I wrote here. But we can use this theorem to help solve polynomial equations, as you've done in pre-calc and algebra, and also to prove some numbers are irrational. At least the algebraic irrational numbers. Example. Let me give you an alternate proof that the square root of 2 is irrational using this theorem. Proof. Note that x equals square root of 2 is a solution to, we found an equation that this was the solution to already. This was x squared minus 2 equals 0. So our a(n) would be 1, and our a(0) would be minus 2. So if a rational group exists, it must be it must be either minus 2 or plus 2. By the rational roots theorem. But radical 2 is not equal to 2, and radical 2 is clearly not equal to minus 2. So it cannot be rational.
Professor, plus and minus 1. Check those two.
Yes, plus or minus 1. Because that's a factor of 2. It's not equal to any of those either. So if a rational root exists, it has to be of this form. This is clearly a root. If I assume it's rational, it must be of one of these forms, but it's not. Therefore, it cannot be rational, because that would contradict the rational roots theorem. So not only does the rational roots theorem help us to solve polynomials, but it also gives us another tool in our toolbox as far as proof techniques go. If I know a certain number is a solution to a certain polynomial, I can use that to my advantage and take the fact that it's algebraic, and I can determine whether it's rational or irrational by looking at the polynomials that it solves. That was one helpful thing. Let's see here. Here's another example. Show that this guy is irrational. So you have that number, you think it's not a rational number? Proof. Note that x equals the cube root of 3 plus radical 7 is a solution to, and here's where, as a math person, you go to the side. do your sketch work, pretend like you knew what you were talking about all along. Oh yeah, that's clearly a solution to this. And how did you get that? No, well, you go to the side. I think this is one we've actually done before. So you cube both sides, and then you take x cubed minus 3, that gives you radical 7, and you square both sides, and so now you have x to the 6 minus 6x cubed plus 9 equals 7, and so you have x to the 6 minus 6x cubed plus 2 equals 0, and so then you go here. Note that this is a solution to by the rational roots theorem, any rational solution to this polynomial must have the form. It can be plus or minus 1 or plus or minus 2. And but now here's the thing. This one is kind of tricky, right? Because it's not, this part is not exactly clear, right? So I can't just say, oh, well, that's definitely not this and that's definitely not this. You might be tempted to say that. But that's complicated enough for you to not be sure. So instead what you would do is you would actually check whether...
Can we just plug it in?
Plug in these ones, right? Now if you plug in these ones, but plugging in plus or minus 1, plus or minus 2 does not solve this equation. So, right, because if you plug in 1, you'll see that you won't get 0. If you plug in minus 1, you won't get 0, etc., etc. So, this guy cannot be one of those. And hence cannot be rational. And you might wonder, well, why couldn't I just do what I did there and just say this is not equal to those? The thing is, because when numbers start looking complicated like that, you're never sure. So hence I'll want to mention here, be careful, some rational numbers can look quite strange. So if there's too many manipulations going on, do not assume that, oh, it's probably equal to one of those. You'll have to prove that. I think I actually gave some examples here. For example, look at this number. The square root of 4 plus 2 radical 3 minus radical 3. And I think, well, that's a very strange number. It turns out it's rational. This is actually equal to 1. So very strange way of writing 1, but it is 1. And that is rational. Another example, it's very similar to this one. You can construct a bunch of these. I use the same method to construct both of them. That is actually 2, which is also. So be careful in sort of saying something like this. Well, clearly this isn't one of these. It's not always as clear. Radical 2, there's only a square root or not. I know that the square root of 2 is not 2. That's easily verifiable. But if things start getting complicated, you have to be very careful in what you throw out there. So rational numbers can look weird, and this is one of the reasons why in some of the proofs that we were doing way back when we were talking about, oh, is this even or odd? When you factor something out and there are radicals all over the place, the thing is you can't tell. You might want to say something belongs to a group or not, but the thing is you can't ever really be sure if things get complicated, then this is why you always wanted to write things such that you know for sure it's an integer, it's just one integer times another, or one integer plus another. And if radicals start coming in the mix, I don't know, it could be anything. Could be a perfect square, could not be a perfect square, could be rational, could not be rational. It can take you some work to prove that. So that's an algebraic number because it solves a polynomial with integer coefficients. It's not a rational algebraic number, however. And I believe I told you last time that the algebraic numbers are countable. So it turns out that most real numbers cannot solve any polynomial with integer coefficients.
How do we go about proving something that's rational? Like proving like that number is rational. How do we go about proving that? You just like solve it?
Yeah, you can say, okay, assume this is rational. Just start squaring things, moving things to the other side. You'd be able to solve for the arbitrary constants. That's the easier case. This is a crazy one. That's all I wanted to say about that. Let's move on to section 3. Here we're going to talk about the set R. R and Q, if you ever wondered what are they, what kind of structures they are, in the mathematical sense, these are ordered fields. Okay. So now I'm going to have to define to you what does it mean to be ordered and what does it mean to be a field. As in, they satisfy the field axioms and the ordered field axioms. Alright, so there's one that introduces order, which is like your less than or equal to, and then there's one that just makes it a field. So let's talk about field axioms first. A set is called a field if it has two binary operations. This means an operation that combines elements of your field, but it combines them two at a time, it means it's binary, which we call addition and multiplication, such that the following properties, let's call this set F, big F, such that the following properties hold for all A, B, C in F. And here are the properties. This is what makes a field. They are defined by our axioms. So the first set of properties, the first four, deals with the addition operation and tells you how that operation behaves. Well, there's a zero element, a zero item, that is, F is closed under plus and times. That is, if A and B are in F, then so is A plus B and A times B. Here's axiom 1 for the addition operation. The addition is associative. So A plus B plus C is equal to A plus B plus C. If you don't change the arrangement, you can move brackets, So it's a binary operation, so we know it only takes 2 things at a time, but what if you have 3 things or more things? The idea is you can group 2 at a time, apply the binary operation here, then apply the binary operation to these 2 results. And you can do this in any order as you're moving linearly. This is called associativity. The next thing for addition is the usual stuff. There's going to be commutativity. A plus B is equal to B plus A. This is called commutativity. So A and B commute with the addition operation. There exists an element 0 in F, and 0 you can kind of take as a notation, such that, I mean, for the real number 0 satisfies this property, but for general fields that might not be the case. So for example, in Z mod 2, the 0 is really the 0 equivalent class. It's a set of infinite number things. But let's actually move on. Such that if you take A plus 0, you will get A. This is called the existence of the additive identity. Another one for addition. For all A in F, there exists someone called a minus A in F. Again, think of that as notation, such that if I take A and I add minus A, I will get the additive identity. So this is the existence of negatives. So those are the properties that the addition operation must satisfy. I'm going to tell you how the multiplication operation what the multiplication operation must satisfy, and how these 2 operations can play together. So here, and 1. So this is the set of operations that multiplication. Multiplication is also associative. And 2. Multiplication is also commutative. And 3, there exists an element which we call 1 in F. Again, for the real numbers, the actual real number 1 is going to satisfy this property, but it might, for arbitrary fields, it might look very different, but we'll still call it 1. In maybe an undergraduate abstract algebra, they might use the letter E to represent the 1, but that's very artificial, and once you pass that class, everyone's just going to write down 1. But you should be aware in very advanced mathematical textbooks, when you see the number 1, it might not be the literal number 1. You have to understand it says some sort of equivalence class for the multiplicative identity. There exists an element 1 in F such that if you take 1 times A, you get A. This is called the existence of the multiplicative identity. And 4, for all A in F, where your A is not the 0, there exists an element A inverse notation, such that if I take A and multiply by the inverse, I will get the multiplicative identity. This is the existence of multiplicative inverses. finally, there's the rule that tells you how these two operations will play together. We know how they play with themselves. We will find how they play together. This is called the distributive law. So there's a rule that we will refer to as DL, and this says that multiplication distributes over addition. Now these are the field axioms, means these are things we will take without proof. We will assume there exist sets that have this behavior. We know that there are sets that have this behavior because the real numbers, for example, has this behavior. And so the axioms, remember what axioms are. These are really statements that should be simple and obvious enough so that we can take them without proof because they seem self-evident. And everything here is really grounded in something that is self-evident, even though it might not seem that way. When you start to write it down in mathematical jargon because you want to be rigorous, things can actually look quite weird. But you should be aware that everything here is based in reality at some point. For example, if you look at the distributive law, I believe I showed my other classes. Why can you say something like that? Well, you can imagine a square or a rectangle where you define what the area of a rectangle means. So let's say one length is A, and this length here is B, and this length here is C. So in other words, that length is B plus C. Then we know that the area is just equal to the length, the height times the base. But also, the area is just equal to the area of this one, and then you add it to the area of that one. Right? So these things, they might look esoteric, and they are because we're writing down them mathematically, but there's a grounding in reality where math people can say, you know what, these things are obviously in existence because I can cut up the farmer's field in this way, and the area will work out when I do both these calculations to the same thing. Therefore, I can make this assertion. In our physical reality, how our universe works, this makes sense to write down. It should be self-evident. So these are the things that are self-evident. There exist sets that have these properties. And a lot of these will come maybe from commerce, right? So you can think of the negatives as debt. And they're like, well, if I'm working with my creditor, this is how money works. I can see it, I can count the pennies, and I can see them being taken away from me, right? So all of these are self-evident. These are called the field axioms, right? So any set that satisfies these properties, we call them fields. R and Q satisfies these properties, right? So that's one thing you should notice. So let's do some examples. Fields, non-fields. R and Q are fields. You'll notice that R and Q will satisfy all these properties. Something that does not satisfy all of them is, for example, the integers. Why? Huh? Because of this guy, right? The integers will fail here, right? If I take the integer 2, what integer multiplied by 2 is going to give me the integer 1? None of them, right? I would need to multiply 2 by a half to get it, but it's not closed, right? A half is not in the original set, therefore the integers would fail. Similarly, the natural numbers will fail. Another field over here is Z mod P, where P is prime. Things over here, Z mod N and non-prime. So if you look at Z mod N, as I described it back when we were doing it in chapter 8, you'll notice that if your N is not prime, it will fail at some of these guys. It will fail even here. While if your N is prime, you're looking at mod a prime integer. That set of equivalence classes will fulfill all these properties, right? But your 0 and your 1 might look different, right? They're actually infinite sets as opposed to just a single element. But the properties will hold. So that's what defines a field. So now let's talk about an order. And And you can restate the field axioms in terms of, in very short sentences after you've done abstract algebra, because some of these properties, there are sets, you can state them in terms of groups, and they can just, oh, it's an abelian group with respect to addition and multiplication, and the distributive law exists. And that's a field. You can say it in literally one sentence. But that will require me showing you a lot of vocabulary from abstract algebra. So you can think of it as just these list of things. So these, I believe it was 9 things, or 10 things including 0, that is what make up a field. So any set with 2 operations that behaves in this way is a field. The real numbers and the rational numbers behave in this way. Let's talk about the ordered field axioms. A field F is said to be ordered by a symbol, and that symbol can change depending on what rules you're giving to this order, and is called an ordered field. So not all fields have orders. If the following hold. For all, do I need 3 letters or 2 letters? I need 3. For all A, B, C in F. So this is called O1, the ordered field axiom number 1. Either A is less than or equal to B, or B is less than or equal to A. So that kind of defines what we call a total order. If you go into set theory, you're going to talk about all different kinds of orders, partial orders, total orders, blah, blah, blah. If you can compare any 2 elements with respect to the order, it's called a total order. So this is technically a totally ordered field. This is anti-symmetry. If A is less than or equal to B and B is less than or equal to A at the same time, then A equals B. The Schroeder-Bernstein theorem actually generalized that. It says it not only works for elements of a field, but it actually works for sets of infinite cardinalities. Which was a little, it's much harder to prove. Here we have it as an axiom for these numbers. We also have transitivity. So if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. O4. If A less than or equal to B, then A plus C will be less than or equal to B plus C. Meaning I can add something to both sides of this thing and it will maintain its order. O5. I can also maintain its order by multiplying by something larger than 0. So if A is less than or equal to B and C is, let's write in a circle, and 0 is less than or equal to C, then AC is less than or equal to BC. And that is the ordered field axiom. So if you have a field, which means you have a set with 2 operations that satisfy the 10 things that I wrote before, it's called a field. If in addition to that it satisfies these 5 properties, according to some symbol that gives me some way to arrange the elements, it's called an ordered field. So both R and Q are ordered fields. And that defines both of them in terms of the axioms. However, we just did chapter 10 from the previous book, and we know that these 2 sets are very different. And you might be wondering, what causes the difference between these? They're both fields, they're both ordered. Why are there so many more of these guys than there are of those guys? And I'm going to tell you the answer. R is different from Q. meaning for one reason. R is so-called complete, in the sense that it has no gaps. We're gonna, or you can say it completes Q. By complete, I'm going to mean, complete in general, if someone says a set is complete, what they mean is that every sequence in that set that converges will converge to an element in that set. The completeness of R is described differently. It's described in terms of the completeness axiom, but that's the next section. That's the next section, right? So the difference between R and Q is literally one axiom, right? So they share 15 things together, but one thing, R has over Q, is responsible for that whole difference. It has one additional axiom. Which we call the completeness axiom. Which is basically implies that R is complete. Any sequence of real numbers that converge will converge to a real number. This is not true for Q. I'll actually specifically talk about this in the next section. But that's the difference. That's the one difference. These are, R and Q are both ordered fields, which means they share 15 axioms together. That one additional axiom makes all the difference between R and Q. If R did not have this, they'll be the same. At least the same number, behave exactly the same in every way. But the thing is, Q has gaps, R doesn't. Q has gaps. I mean, you plot the Q's on a number line, you take a sequence that jumps from one element in Q to another, make sure it converges. It might not converge on an element of Q. It might converge between two elements of Q. And this is super small. Like, we have the density of Q property, which tells you how small these gaps are. But when you take all these gaps and add them all together, it makes up an uncountable set. Let's actually look at some consequences of these axioms. So here are some things that you might think of as axioms because they seem so natural to you and you've taken them for granted. The field axioms. But they were not assumed. These things had to be proven at some point. There. A, B, C are elements of F, a field. Then 1. If A plus B is A plus C, if A plus C is equal to B plus C, this means that A is equal to B. Who would have thought, right? Right? But that's not an assumption. That can be proven based on the previous things. Here's another thing that can be proven. If you take something and you multiply by 0, the answer will always be 0. That's not something that's obvious. That's something that had to be proven. Here's another one. Minus A times B is equal to minus AB. I can factor out negative signs, which is quite strange. Something else that's interesting. Minus A times minus B is equal to AB. So if you guys saw that movie Stand and Deliver, where he was shouting to the kids, a negative times a negative is a positive. A negative times a negative is a positive. They're all chanting, and then everyone's getting, and then he says, why? Whatever. Yeah, this is why. It's actually something that can be proven. Right? That's not something you take for granted. That's not obvious at all. Well, I mean, it feels obvious because you were indoctrinated as children, but it's not obvious. If A times C equals B times C and C is not equal to 0, then it turns out that A equals B. Right? In other words, you can cancel. This is the cancellation. That's the thing that allows you to solve 2x plus 1 equals 0 for x. It's the cancellation. Another one. 5. If AB equals 0, then A equals 0 or B equals 0. So if I multiply two things and I get the additive identity, one of these two things must be the additive identity. And again, you should be reasonably convinced at this point that that's not obvious, because we actually did an example in C mod 4 where that was not true, right? The equivalence class of 2 times the equivalence class of 2 gave me the equivalence class of 0, but neither one of them was the equivalence class 0, right? So that, again, not obvious. Why it didn't work in Z mod 4 is because Z mod 4 is not a field. But for a field, this will always work. So that thing when you factor a polynomial, say equal to 0, and then you set each factor equal to 0, not obvious. You can only do that if you're working with a field. If you say your x values are not elements of fields, you could not solve the polynomial that way. So that's a theorem. A lot of manipulations that you might feel natural to you, they might feel axiomatic, might feel like God's dropped it to us from the sky, but no, it's something that we can prove. Right? We looked at our field, we diced it up in a bunch of ways. Oh, this is a rule. Hey, that rule says this can happen. That's kind of where it came from. Here's another theorem. Let F be an ordered field. A, B, C, elements of F, then this is true. If A is less than or equal to B, then minus B is less than or equal to minus A. 2. If A is less than B and C less than 0, then BC is less than or equal to AC. That's the guy that tells you when you multiply both sides of an inequality by a negative number, it flips the inequality. Here, if 0 is less than or equal to A, so A is positive, and 0 is less than or equal to B, then if I multiply these two things, I maintain being greater than or equal to 0. A direct consequence of that is that 0 is less than or equal to A squared for all A. Right? Again, something you might have taken for granted. Oh yeah, x squared is a real number, it's always greater than or equal to 0. Not obvious, that had to be proven. Right? You can use this to prove that. Right? Just take A equals B in the previous one. So once you prove this, take A equals B, you get this right away. But it's not obvious. Here's one. 0 is less than 1. i.e., 0 is less than or equal to 1, and at the same time, we know that the 0 is not 1. How would we know that the 0 is not 1? Because when I multiply by 0, I don't get the original back. Right? That was proven in the previous theorem. So by definition, my 0 cannot be equal to the 1. My multiplicative identity will not be equal to the additive identity. 0 is less than A implies 0 is less than its inverse. So you take the reciprocal of something and it's positive, it will stay positive. 7. 0 is less than A, less than B, then you might have also noticed that if you take the reciprocal of both sides of an inequality and the both sides have the same sign, you have to flip the inequality. And this is why. So these are theorems. They're things that you should not take as obvious. These are things that had to be proven at some point. Your book proves a lot of them, and there are others to prove in the homework. I don't remember which ones it proves, but let's I don't want to spend a lot of time on this, so let's prove one. Let's show that I can factor out this. We show this is true. So here's something. 0 is equal to 0 times b by 2. Okay? So I'm proving 3. Which I have to prove 1 and 2 to get to 3. Okay? So let's just, I can use anything from 2 and above all the field axioms and anything. Okay. So 0 is equal to 0 times b. Sure, this says a times 0, but we know that multiplication is commutative by the field axiom, so I can write it as 0 times b. I could also write b times 0, but I just want to write it as 0 times b. 0, by definition, is going to be minus a plus a, right? A is an element of the field. It has a negative. When I add something to its negative, it gives me, so this is by field axiom. I forgot one number. 4. So field axiom 4. This means this is equal to minus a times b plus ab by the distributive law. But now, if we add this guy to this guy, we get 0. This means that this guy is equal to the negative of that by axiom 4. Right? What I've just shown is that if I add this guy to that, the result is 0. It must mean this guy is the negative of that, right? The existence of a negative, which means I can write this as just minus this. So that's one example. So after proving this one should be easier. Just replace things with minus b instead, and you get the fact that a negative times a negative is a positive. Another common one to prove is that we can do this. If you assume that a times b equals 0, but one of them is not 0, so if you assume, for example, that a is not 0, then there's a multiplicative inverse that I can multiply both sides by. It will cancel, and then I would end up with b equals 0. So one or the other has to be 0 if the product is 0. Right? So none of these were obvious, they had to be proven. The textbook will prove some of them and ask you to prove some of them in homework, so let's actually just move on. Because there are other proofs that I want to do, and we're already sort of behind time. Let's actually see really why the real numbers are different from fractions. This is section 4, the completeness axiom. So both R and Q are ordered fields, but R is different. R is a lot larger, So the difference is this, and I think I probably need to talk about some definitions first. Let S be a subset of R. M in S, if it exists, is called a maximum element of S, denoted max S, if M is greater than or equal to A for all A in S. Assuming our S is not empty. Another definition. S subset of R, non-empty. Little m in S, if it exists, is called a minimum element. If n is less than or equal to A for all A in S, we write n equals min S. Definition. Let S be a subset of R, we're assuming it's not empty. If there exists an n in R such that it may or may not be a member of S, but such that n is greater than or equal to A for all A in S, then n is called an upper bound of S. And S is said to be bounded above. Let S be a subset of R. If there exists an element of R such that that element is smaller than or equal to A for all A in S, then M is a lower bound of S, and S is said to be bounded from additive. If S is bounded from above and below, it is called bounded. Right? So there's bounded from above, bounded from below, and bounded in general. Bounded means you can bound it on both sides. Bounded from above means there's an upper bound where elements will not pass, and bounded from below means there's a lower bound that elements will not pass. Okay, so you can talk about bounded from below, bounded from above, or bounded in general. So we need that definition to talk about supremes. When do you talk about that? Let's wing it. I think at this point we can introduce the supremum. So now let's talk about it. The completeness axiom. It says simply, every non-empty subset of R bounded from above has a least upper bound. Which is an element of R, by the way. That's it. That's what makes R different from Q. Every subset of R that is bounded from above will have a least upper bound. There will be a real number that is an upper bound, and there's no other upper bound smaller than that number. The least upper bound is called the supremum of S written sup S. It's pronounced sup S. To be a little bit more specific, suppose S subset of R is bounded above. Then there is an element which we denote sup S in R such that 1, sup S is greater than or equal to S for all S in S, and 2, if M is greater than or equal to S for all S in S, then, right, so that means M is some other upper bound, then your M must be less than or equal to the sup, greater than or equal to the sup. So it is an upper bound for the set, but it's the smallest one. So if you tell me some other upper bound, this guy's always less than or equal to that upper bound. And such an element is called a supremum. I don't know if this is conversely, but whatever. Conversely, so this is not the axiom. The axiom is just stated in terms of upper bounds, but you can actually prove it's true for lower bounds using a very similar trick that we've shown. We've actually done it in homework where you just took the negative of everyone, showed that that had an upper bound, but it ended up being the lower bound of the original set. So using a similar proof to that, we know that every S subset of R bounded below has a greatest lower bound. Meaning it is smaller than or equal to every element of S, and if there's any other real number smaller than or equal to every element of S, if this guy is greater than or equal to that guy. We call this the infimum of S, denoted inf S. So that's a consequence of the completeness axiom. So let's do an example. Yes.
I'm still very lost as to how you can have an n greater than your suprema S that is also within your set S? Or would the n not be included in the set S at all?
It might not be included. For example, if I take 0, 1 subset of R, then 1 is the supreme.
But it's not within the, okay.
Right? Now, you can tell me any other number, 5. It's an upper bound for that set. This is smaller than or equal to that. 7. It's an upper bound for that set. This is smaller than or equal to that. 1. Well, it's actually equal to that. Right? No matter what number you call that is also an upper bound for that set, it's a real number that's larger than or equal to everything in that set. It will actually be, this will actually be less than or equal to that. So you would notice here, 1 is not necessarily an element of the set. Now, versus, if I said something like 0, 1 as a subset of Q, all the rational numbers that are strictly greater than 1, 0, less than or equal to 1. That'll actually work. Versus, look at this, the set of all R in Q such that R is bigger than 0, but it is less than radical 2. What is the least upper bound of that set? Radical 2, but that's not a rational number. Right? Here, least upper bound is radical 2. But we've proven many times by now, radical 2 is not a rational number. Right? So that's the difference between R and Q. I can look at subsets of R that are bounded, and I would be able to find a least upper bound that's still in R. For Q, that's not doable. And that's what they mean. Q has gaps. So if I look at the set of all upper bounds of subsets of Q, not all of them are in Q. Some of them are blind. Q is blind to these numbers. Right? They're a gap in the number line. Q says, yeah, we're inching towards this thing, but I don't know what it is. It's not one of us. Right? So that's what they mean. There are gaps. So you can look at the number line between 0 and radical 2, and you can have rational numbers inching towards radical 2, but the thing is they'll never actually be there. There's a hole here that a rational number cannot fill. So that created a gap in the number line, right? And what R does, it fills in those gaps. And there are a lot of rational numbers, there's an infinite number of them. But there's also an infinite number of gaps. There's an infinite number of guys that have these gaps. And when you add up all these gaps, you get an uncounted set. So there are more gaps than there is line with respect to Q. Which is weird, because I've already mentioned in test, and I'm going to mention again, between any interval that you pick, there's a bunch of rational numbers there. So the fact that no matter where you are, you can find a rational, and at the same time there are so many gaps that they outnumber the rationals is kind of mind-boggling, but that's what you get when you have infinite cardinality. Two important theorems here. It's called the Archimedean principle. Another thing, I don't actually know if Archimedes was the guy that came up with it, but it's named after him. I should probably look that up. And I probably spell Archimedean wrong, but whatever. This is an English class. Okay, so if A, B are real numbers and they're both positive, then there exists some n in the natural numbers such that if I take n times b, it will be bigger than n times a. This is called the Archimedean property. Okay? Give me any two positive numbers. There is a natural number such that the n shouldn't be on both sides. Such that I can take the natural number times either one of them and exceed the other. And it doesn't matter where you start, right? So I can say, suppose b is 1 and a is a billion, right? So a is clearly bigger than b. But no, there's some natural number that I can multiply the b by so that it will pass the a. Right? This is called the Archimedean property. Right? In that example, I can just multiply this by 1,000,000,001. And then it will pass the a, right? But that's not always clear. That's not exactly obvious that why you can do that. Do I have time to prove this? I do. Maybe I'll do a proof outline. If you assume that a greater than 0, b greater than 0, but there is no such n. This means that n times b will be less than or equal to a for all n, right? Because that's the opposite. So the set NB is bounded above. Right? There's a number that's always greater than or equal to everyone. Therefore, it has a least upper bound because we are in the real numbers and that is an axiom of the real numbers. Let S equals the supremum of this set. The supremum of all things that looks like that, such that that is an attribute. Then I know that S must be less than or equal to A. Right? And on top of that, also, if I take S must also be less than or equal to that, right? So I take S and I add a positive number to it. It is bigger than the original S. And so where do we go from here? I'm rushing and I'm losing my thought because I'm rushing ahead in my head. Okay. So if that is the case, this means that S minus A is less than S, and so S minus A is not an upper bound. I can even put less than here to make it much more obvious. That will clearly be true. Okay? So this number is less than S. S is the least upper bound, which means that this expression cannot be an upper bound. So there exists some n natural number such that if this is not an upper bound of that set, that means that there is someone in this set that's larger than that. Such that S. Okay. So here's where I was rushing. Okay. I'm going to call that B. I think now we should have it. Such that S minus B must be less than n times B. And that would mean S is less than or equal to n plus 1 times B. So there exists X in that set. Let's call this big S, such that it is larger than the supremum. And that's a contradiction. Archimedean property, this is used all over the place. It's super useful, especially when you're really starting at the beginning of number theory and really building up the real numbers and all the properties that you know and love from algebra class, this is one of the guys that gets you very far. And you can prove it using the completeness axiom. Right? So if you assume that this is always true, then you can get a contradiction just by identifying the supremum, finding something that's not an upper bound, and then showing that that would imply that the supremum is less than or equal to some element of the set. And this follows from the piano axioms, right? Because if n is a natural number, then n plus 1 is also a natural number. So this guy has to be in there. So I found an element in here that is larger than the supremum. That's a contradiction. The supremum should be larger than everyone. Here's a consequence. I mean, it's a theorem in its own right, but it's because it's very important. But it's kind of a corollary to this, the denseness of Q theorem. I.e., it's also the phrase you might say Q is dense in R. Meaning, if you go to the real line, take any subset, any interval on the real line, you will find a rational number in that interval, right? So they're countable, but they're spread out, right? So we say they're dense in R. I.e., if A, B are elements of R with A less than B, then there exists a rational number Q such that it is strictly between A and B. This means it's dense in R, right? I don't care how close these numbers are together, 0.1 and 0.0999991, right? In between them, you can find a rational number, right? So any two real numbers, no matter how close together, as long as they're not exactly the same, there's a rational in between there, right? So the rationals do not fill in all the gaps on the number line, but they're kind of everywhere at the same time. They're everywhere, but not everywhere. Infinity is such a weird thing. Okay, so that was the denseness of Q property. Now, in the first test, I asked you guys to actually assume this and show that, you know, there's actually an infinite number of rationals between those two, right? Which you could prove by induction or a contradiction. Okay, but let's actually show the theorem is true, that we know there's at least one. And again, kind of rushing, so I won't be too pedantic here. Proof outline. Assume A is less than B. Then, again, we're applying field axioms and all that. I'm not going to say that. So that means that B minus A is positive. Since 1 is positive, that's also an ordered field axiom, but okay, let's throw it out there. We can apply the Archie principle. Yeah, I can call him Archie, we're tight right now. To the numbers B minus A and 1. So there exists some natural number n such that I can take n multiply B minus A and it will exceed 1. Right? No matter what that guy is, it's positive. Even if it's super small, 1 over a trillion, there's a natural number I can multiply that by such that it will eventually be bigger than 1. This means that NB minus NA is greater than 1. So the interval, in particular what I'm saying is the interval NA and B has length larger than 1. Which means there has to be an integer in that interval. Right? Again, that's something you sort of have to justify. There are a bunch of ways to do it. Probably the easiest is contradiction. Assume there is no integer in that interval, then all integers fall outside that interval. So that would mean there are two consecutive integers that are more than 1 unit apart. Contradiction. Okay. So, but eventually by saying that you can say, then there is some m in Z, so that if I take the NA, the M is between those two. Divided by N, we get M over N is between A and B. Right? So clearly found some. I found a rational number that's between A and B. N is in N, so it's non-zero. And so I just found a ratio of integers that is where the denominator is non-zero. So any two real numbers, there is a rational number in between them. In fact, there are infinitely many. That you need sort of induction though, or something similar, something a little bit more esoteric. But yeah, assuming that R fills in all the gaps is the same as assuming that a supremum exists for every upper bound. That implies the Archie principle. The Archie principle implies the denseness of Q, and you get a lot of things. So Q is a lot smaller than R in terms of cardinality, but it's dense. It's spread out all over the number line. Any interval you look at will contain rational numbers, but there are not as many of them to fill in the gaps. In fact, they leave so many gaps out. The gaps outnumber themselves. And actually, how are we on time? Actually, kind of okay. So let's just. I think those are the main ideas I wanted to cover. I feel like I skipped some examples because I lost my notes. But those are the main ideas, right? So, here's an idea. Show that if I take R minus all the integers, it makes no difference to the number of things there. How would you show that? Right, so I mentioned that last class, so I never really gave you a proof, I just kind of threw it out there. What are the ideas?
It's R is uncounted.
Huh?
R is uncounted.
Okay.
Integers is counted. How do you show that?
Yeah, that's why I'm asking you guys. How do you show two cardinalities are the same in general? Huh? There's a bijection function from one to the other. I'll tell you right now, it's going to be hard to find the function. There are functions that exist and there are people that have found them, but try to not use that. What's another way we know how to prove the cardinalities are the same? Schroeder-Bernstein. Right? So Schroeder-Bernstein says if this one is less than or equal to that one, and this one is less than or equal to that one, then they must actually be the same. So you can do that. A consequence, I don't remember if I said this, I should have, but it's fairly obvious, so it's almost like a one-line proof to show that the identity function satisfies the injection. But if A is a subset of B, then that should be clear. Right? Because there's a one-to-one function from this to that, just send every element here to itself. So it's even easier in the sense that there are times when you don't have to actually show an injective function to prove even that. You can just do things in terms of subsets. But obviously, this guy is a subset of that. It's not exactly clear that the other way is true. So ideas, can you bound it? Show.
Can you, well, you mentioned bounding it. Can you look at it only over a specific interval? Or would that?
Okay. Choose what interval?
Just between two consecutive integers, so that the in-between would be the same for both sets.
So
For example.
consider.
Consider zero to one.
Consider. Wow. Like how did you come up with that? No one. We might never know. Consider that interval. Okay. What can you tell me about that interval, and how are you going to relate it to this?
Well, you can create a bijective function over that interval from r minus z to. Oh. Well, you can. Could you do one from that interval from 0 to 1 to r minus z, and then also to r?
We don't. We don't know the function. What do I know about 0, 1?
It's uncountable.
It's uncountable. How many elements is it? It's actually the same. No. The size of that one interval is the size of the whole thing. Okay. Which is super counterintuitive, but whatever. And that's actually true. We actually did a function, right? The arctangent, the tangent function. We can go for many functions. This one is easy to find a function for one together.
Since that's a subset of your r minus z, can you just?
Yeah, but at the same time, if this guy here is a subset of r minus z, right? It is a bunch of real numbers that are between two consecutive integers. So if I throw away the integers, it's not going to affect anyone in that interval. And so this means that the size of this guy is less than or equal to the size of that guy. And so now how do we finish up?
They have the same kind of elements.
Isn't r minus z a subset of r?
R minus z is a subset of R. So this is less than or equal to this. Right? Since this guy is a subset of that guy. But this we know is actually equal to that. So that means that the size of R is less than or equal to the size of this, which is less than or equal to the size of this. Then you apply, well, normally we would say the squeeze theorem, but we could actually apply the field axioms here. That means that R minus Z is the same size. So one infinity is so much bigger than another infinity. You throw one away, you still have, it made no difference. Yeah.
Well, I wanted to ask before if we were allowed to say something along the lines of like, we know like the cardinality of Z is alpha naught. So
Okay.
can you make the argument that R minus Z would be greater than alpha naught, so therefore must be equal to or greater than the cardinality of R? Or the continuum?
What statement do you want to prove?
Using the
Do you want to say R minus Z cardinality is greater than alpha naught?
using the well, I was just wanted to ask if you could use the continuum hypothesis at all, since you said that can't be proven or disproven, but
Oh yeah, we take the continuum hypothesis as a fact.
so could you say
We don't know if it's true or not technically, but it's assumed.
so could you then say that since that is obviously greater than alpha naught, it has to be equal to or greater than the continuum, or the
Yeah, if you apply the continuum, yeah. So you say it has to be the continuum or bigger, and then if it's bigger, you get the other side of that. You get it smaller than or less than the same thing. Yeah. Yeah, so you can just start off your proof. We take the continuum hypothesis as proof, and then you can make that argument. Yeah. Anyway, that's it. That's all we have. As I said, we'll post a take home over the weekend, maybe Sunday, bring it to class on Tuesday. And that's it. Well, we don't have class on Tuesday. So if you don't see me, you can drop it in my mailbox, which is in the math department, NAP 8133. So NAP 8133. Let's go to my mailbox, which is Smith. There should be someone at the front desk. They just put it in my mailbox, and then I'll be around, but I don't know if I'll be in one place. My 346 final is that day, so I'll definitely be around. Anyway, have a good weekend.